Depth perception. The world is three-dimensional, 3D, but the images cast onto our retinas vary in only two spatial dimensions, vertical Y location and lateral X location. The third dimension of depth, or Z location, is missing, yet this dimension is crucial for many visual tasks, such as reaching out to pick up objects, walking over uneven terrain, or assessing how far away a dangerous predator may be. The visual system has to build the three-dimensional representations of the world from the two-dimensional images that it receives. Four important computational goals of depth processing are to establish the depth order of the visible surfaces, which is nearest, which is furthest, and so on. Estimate the depth intervals between surfaces, how much further away one surface is than another. Estimate the absolute distance of surfaces and objects from the viewer, and derive estimates of three-dimensional surface geometry and object shape. And many objects and everyday activities require perceptual judgments of three-dimensional depth and distance. Just thinking about running, for example. To complete these tasks, the visual system must use clues and available in the two-dimensional retinal image and in the state of the muscles both inside and outside the eye. There are multiple cues that are available, which vary in their utility for completing the different tasks. We can have cues to depth and their relevance to the four computational goals listed. Of course, the most basic task is to determine depth order, and all cues can contribute to that. Most cues can also supply some information about depth intervals, but relatively few are useful for estimating absolute depth, and surface shape. However, the devil is in the detail. The utility of each cue is limited in certain aspects, such as in terms of the ranges of distances over which the cue operates. The following discusses each cue in terms. Of course, we have interposition, utility of depth cues and depth computations. We have depth order, depth interval, absolute depth, and shape. And so it is only with stereo invergence we have both absolute depth, shape, depth interval, and depth order, as well as although we have depth order, depth interval, and depth and shape, but not absolute depth with shadows. And then, of course, we have, well as shadows and motion. Accommodation, for all of these, accommodation, blur, texture, gradient, size, atmosphere, height, and interposition, they all give depth order, depth interval, but no absolute depth, and only texture gradient gives shape. Monocular depth cue is a depth cue available when only one eye is used. It is also available using two eyes. Binocular depth cue is a depth cue available only when both eyes are used together. Interposition is a monocular depth cue based on partial occlusion of a far object by a near object. And then HVF is height in the visual field, which is a monocular depth cue based on the vertical position of a point in the visual field. Higher positions correspond to further distances. And, for example, you could imagine height in the visual field of an object on the ground surface as a function of its distance from the viewer, assuming a horizontal ground plane and fixation on the horizon. Then we have what's called ordinal depth cue, which is a depth cue in which cue value varies in discrete ordinal steps, such as nearer versus further. And then texture gradient, which is a monocular cue to the orientation and depth of a textured surface. It is based on graded variation in the size, shape, and density of texture elements. And Leonardo da Vinci, for example, was a pioneer in the use of atmospheric perspective in his paintings. He developed a technique known as sfumato, which is smoky or hazy in Italian, which involved the application of thin, translucent glazes to reduce contrast and so to create a sense of distance. And so we've gone over There's retinal image size, atmospheric perspective, texture gradient, image blur. Depth of field is the range of distances either side of the point of focus within which there is no perceptible blur in the visual field. So image blur can be used as a depth cue. Then there's accommodation. The range of accommodation shrinks with age. By the time that most people reach their 50s, there is virtually no accommodative range left due to the loss of flexibility in the lens, hence the need for reading glasses. And, of course, then there's motion parallax, which is movement in one part of an image relative to another, as can be produced by objects moving at different distances from the observer. Motion parallax provides powerful depth cues. And then, of course, there's shadows. Texture and shape cues provide a 3D context for the spheres, but each sphere apparent position in the scene is influenced by its cast shadow, for example. So you can use shadows to act as cues. And then binocular disparity, as well as vergence, which vergence and binocular disparity are binocular cues. Again, binocular cues are two depth cues that are available only when information from both eyes is combined. One cue is non-visual, which is vergence, and the other cue is purely visual, which is binocular disparity. Vergence angle is the angle at which the visual axes of the two eyes intersect while the observer fixates on a point. Binocularly, it offers a cue to fixation distance. The top eyes must converge to fixate on a near object, and we might want to analyze a painting of an outdoor scene in terms of the cues used by the artist in order to convey an impression of depth. And of course, horizontal binocular disparity is a binocular depth cue based on the difference in the horizontal retinal position of an image point in one eye relative to the other. It is often abbreviated to disparity. And then we have far disparity and near disparity. The horizontal binocular disparity created by an item that is further away than fixation distance. It is also known as uncrossed disparity, that is far disparity, and then also known as crossed disparity, which is near disparity, the horizontal binocular disparity created by an item that is nearer than fixation distance. And so there we have far uncrossed disparity is the non-fixated point is further away and the right eye's view of the point is shifted to the right relative to the left eye's view. And near crossed disparity is the non-fixated point is nearer and the right eye's view of the point is shifted to the left relative to the left eye's view. The magnitude of the disparity, or in other words, the magnitude of the shift in position of a non-fixated point in one's eye's image compared to the other eye's image, depends on the difference in distance between the fixated and non-fixated points. And, of course, we have vertical disparity and random dot stereogram. Random dot stereograms, or RDS, is a stereogram containing pseudo-randomly arranged dots. Some dots are in disparate locations in one eye's view relative to the other eye's view. And, of course, we have what's called the correspondence problem in RDS. Again, RDS is random dot stereogram. The correspondence problem is the problem of matching up two images point by point. The two images may depict the same scene at different viewing positions or times. The epipolar plane is the plane that passes through a given point in front of the viewer and through the nodal points of the two eyes. The epipolar line is the projection of the epipolar plane onto the retinal image. And diplopia is double vision. It is when the observer sees two images of the same object simultaneously. Diplopia. So at very large or small disparities, vision tends to become diplopic. We see double images. To demonstrate the effect, fixate on the end of a finger held about 30 centimeters in front of your eyes. If you direct your attention to objects further away while maintaining fixation on your finger, you will see two images of each object. Similarly, if you place another finger much closer to your eyes, it will also appear diploptic while fixating on the more distant one. And then you could have cue combinations. You could have correlations between cues and combining cues. For example, neurophysiological evidence indicates that the neurons in higher order cortical regions integrate information from different cues. And so, it can vary. Depth cues can be often incomplete, imprecise, or even contradictory, and the cues are vary with the context, obviously. So interposition is an unambiguous about ordering but cannot specify depth interval. Size cues rely on knowledge about real size. Texture gradients are available only in scenes containing evenly textured surfaces. Image blur varies with ambient illumination or pupil diameter. Accommodation varies with age and refractive state of the observer. Motion parallax cues are available only when the objects of the observer move, and horizontal disparity cannot specify absolute distance. We might want to think of some other factors that might influence the weight attached to particular cues. And no single cue is adequate by itself, and different combinations of cues are relevant for different tasks. And so the visual system adopts a flexible strategy in which cues are combined with variable relative weights depending on the context and task. And of course, to sum up, we talk about the computational goals of depth processing, which is to establish the depth order of the visible surface. That is the first. The second is to estimate the depth intervals between surfaces, and then to estimate the absolute distance of surfaces and objects from the viewer, and then deriving the estimates of three-dimensional surface geometry and object shape. The multiplicity of depth cues. There is a wide range of cues that can provide information from depth processing. On a monocular cue level, it would include interposition, height in the visual field, atmospheric perspective, retinal image size, texture gradient such as height, width, and density, image blur, accommodation, which is a non-visual cue, motion parallax, and shadows. Binocular cues include vergence, which is a non-visual cue, as well as binocular disparity. But all cues have limitations that constrain their support for depth computations. Concerning cue combination, most cues provide quantitative information about depth but vary in their relevance to different depth computations. And so the visual system combines information from different cues in a complex, flexible, and idiosyncratic way, and research indicates that the visual system takes the weighted averages of the estimates provided by the different cues. Cue weight varies according to stimulus, conditions, task, and the observer, him or herself. I think we have spoken a little bit about stereograms, which is an image designed to create an impression of depth when viewed binocularly. Different parts of the image are seen by the two eyes, however.